All gravity wells accumulate matter. Eventually, every system pulling in chaotic, dark material organizes into coherent, structured emission. Observing this process requires comparing systems that have virtually nothing else in common. We have to map a 0.6 solar mass white dwarf against a billion solar mass active galactic nucleus. To establish a baseline, astrophysicists use the Eddington ratio. This metric compares a system's observed luminosity against the maximum theoretical output it can sustain before radiation pressure blows the infalling matter away. When applied across different object classes, the Eddington ratio spans 10 orders of magnitude. It fails to provide a single, consistent boundary defining the exact point at which a quiescent system ignites into an active state. Without a unifying metric, the onset of emission has long been treated as a product of local environmental factors, gas density, magnetic fields, and local composition. There has been no single, predictable law for activation. Independent researcher Monty Brocco proposed a solution through a mathematical transformation. He converted the sprawling Eddington ratio into a bounded entropy coordinate, designated as S. This plots the entropy coordinate for 790 active galactic nuclei. Blue quiescent and red active sources split at a single vertical line. Below, white dwarfs and neutron stars align to the exact same line without modifying the scale. That boundary sits precisely at the value of 1 divided by 4 pi. In decimal form, that is roughly 0.0796. A pure geometric fraction correctly separating the active and quiescent states across millions of solar masses points to a physical geometric boundary condition rather than a statistical coincidence. We can trace exactly how this geometric fraction emerges from the standard observational data. The Eddington ratio is semi-infinite. It scales upward boundlessly. The entropy coordinate transforms this metric. It compresses that entire scale into a strict, bounded domain between 0 and 1. The formula dictates S equals lambda over lambda plus kappa. Kappa is calibrated at 0.176 using 30 black hole transitions. This satisfies an independent relation. It equals 4 pi minus 1 multiplied by the ADAF threshold, Liddencrit. Substituting this relation back to solve for the boundary, lambda crit appears in both numerator and denominator. The specific mass variables cancel out. The substitution clears, leaving only the pure fraction. S crit equals 1 over 4 pi. Because the terms describing mass, scale, and environmental variables mathematically cancel out, the remaining threshold operates exactly the same way, regardless of the object's size. A mathematical derivation only holds weight if it maps cleanly onto real multi-wavelength catalog data. This chart plots the entropy coordinate across all mass ranges, spanning from a tenth to 10 billion solar masses. Above the dashed 0.0796 line, red points represent active systems. Below it, blue points mark systems remaining in quiescence. Every point on this plot was calculated using the exact same kappa constant. Parameters were not adjusted, refitted, or scaled for the different object domains. The identical mathematical boundary accurately predicts the emission state of a stellar mass white dwarf and a distant supermassive black hole. The strictest way to test a threshold is to track a single distinct physical object as it transitions between its quiescent and active states. Look at the individual bar graphs mapping these states. In the isolated panels for white dwarfs and X-ray binaries, the blue bars sit entirely below the threshold line, and the red bars reach entirely above it. Evaluating historical data for X-ray binaries yields 14 out of 14 accurate separations. In every recorded instance for these pairs, the quiescent state maps below the line, and the active outburst maps above it. Observational data of the neutron star 4U0614 plus 091 caught the object crossing the exact 0.0796 boundary at the precise moment its accretion behavior shifted from low to high states. A mathematical constant that captures both the sudden outburst of a single binary star and the multi-billion-year activation of a galaxy is a direct observation of scale invariance in accreting matter. The observational data aligns with the model. The next step is identifying why the specific fraction of 1 over 4 pi governs astrophysical accretion. The equation for the surface area of a sphere is 4 pi r squared. The threshold isolates a specific segment of that spherical boundary. Brocco's constant defines the minimum coherent information density required on a spherical boundary. When infalling matter achieves that density, the system crosses the threshold, and disordered inflow reorganizes into structured emission. This exact fraction appears in established thermodynamics. It acts as the proportional factor in the Bekenstein-Hawking equation, establishing the minimum information density required for a horizon to encode degrees of freedom. Its recurring presence links the activation of astrophysical accretion directly to the thermodynamic limits of spherical information horizons. If a strict geometric boundary mandates a phase transition, we must evaluate how this applies to the ultimate endpoint of gravitational collapse. As the accretion rate increases toward infinity, the entropy coordinate climbs, approaching a hard ceiling of exactly 1. A classical singularity requires reaching that limit, but as matter falls inward, the coordinate must pass through the 0.0796 boundary first. Triggering a phase transition at this lower threshold, every accretion flow reorganizes into coherent emission before ever reaching the theoretical density of a singularity. In this framework, the event horizon functions as a physical phase boundary. It is the point where infalling matter achieves the critical information density required to fundamentally reorganize into outward-flowing energy. Brocco's threshold is a universally predictive, instantly falsifiable geometric law that reframes decades of disconnected astronomical data into a single, elegant mechanism of astrophysical emergence.